Now, dear friends and students, let's talk about quantum numbers and have some understanding of quantum numbers. And and I would like to start with the principal quantum number, and and what is so important than that of principal quantum number is that this quantum number is very much linked with the quantization or discreteness of energy. So it is linked with quantization or discrete discreteness of energy. And so to speak, and so to talk about is that uh, that 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 if I assume the quantum the quantum number that signifies the hydrogen atom in terms of classical model of atom. Uh, if we go to the classical model of atom, that's very much equivalent to that of planetary motion in the solar system, where you have a nucleus and you have electron orbiting around this nucleus, with only one difference, that in case of planetary motion, what we have is the gravitational inverse square law, and here we have electrostatic. Here we have electrical inverse square law, electromagnetic inverse square law involved, and and to hold. There happen to have two quantities that have to be conserved, and that have to be conserved all the time in the planetary motion. And what's that is that we must have some total scalar energy, or scalar energy, and it can have any value. It can have any value, whatever. But certainly, uh, it must, of course, be negative if the planet is to be trapped permanently. So, if you have to talk about the total energy uh, regarding a planet that's moving around the sun, and what's important is that its total energy must be negative. So to be trapped in the solar system permanently. And in quantum theory of hydrogen atom, the electron energy is also constant. We have constant electron energy, and at the same time, it may have any positive value. It can have positive value corresponding to ionization. Ionization, we understand the energy that's given to the electron, so that the electron will completely miss the atom. So the energy that you can think in terms of positivity will cause ionization in atomic levels. And so to say, so to be precise, is that we have, in case of atomic world, we have found that this energy En is E1 square by n square, where this E1 is already it's having some constant value that has been incorporated in the previous video. So the quantization of electron energy in the hydrogen atom is therefore described by this n, and this n is called as the principal quantum number. That should be the case. And And at the same time, if we have to talk about the planetary system that we have, and if we apply Schrodinger's wave equation to this planetary system, where a planet is revolving around the nucleus, it will yield the same or similar kind of restrictions. But the fact of matter is that the total quantum number we will have for any of the planets uh, uh, turns out to be extremely large, extremely large, and that value can be calculated as well, and that it's impossible to have a differentiation of one energy level with respect to another energy level. It's impossible to separate out these permitted levels that can be calculated when Schrodinger's wave equation is applied on this planetary system. And this may be the reasons that the classical physics provides. It provides adequate, it provides a complete description of planetary motion, but it certainly fails within the atomic domain, where we have quantization, and where we have discrete values of energy. So this n that we have from this energy equation, this n gives us the quantization, and this n is termed as principal quantum number. Now the next important quantum number is the orbital quantum number. The orbital or orbital quantum number. And we have already written down the differential equation in terms of the wave function r for this orbital quantum number. Okay, so we can. So here we have the equation for this for the what we call as the radial part of the hydrogen atom that we have. If I write down this equation, what is it? It is 1 by r square d by dr of r square dr by dr. Then we have plus. Then we have 2m by h cross square times e square by 4 pi epsilon naught r. Then we have some plus e. Then we close it. Then we have minus l times l plus 1 by r square. Then you close it. There's a wave function r. This is equal to 0. Now, if we look onto this differential equation, we have this differential equation for the wave function r, and this equation is certainly concerned with the radial aspect. It's concerned with the radial aspect that's involved in the hydrogen atom, and as long as the motion of electron is concerned, that's its motion towards or away from the nucleus. And at the same time, what we notice is the presence of E. And what is E? E is the total energy here. We have total energy, E. E is the total energy in this equation. And this total energy, E, what it includes basically is the electron's kinetic energy. It includes the kinetic energy of electron due to the orbital motion. And what it does is it has kinetic energy of an electron due to its radial motion. So we have two kinetic energies involved here that incorporate the total energy, and one is the orbital motion of electron. So we have the kinetic energy due to the orbital motion of electron, and the another is the radial kinetic energy that is linked with this electron. So so the argument is here that this total energy includes it includes the kinetic energy of orbital motion, and it includes the radial energy of the electron due to its motion towards or away from the nucleus. And 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 talking about the potential energy that we have, if we talk about the potential energy, which is here, which is V, and this V is minus E square by 4 pi epsilon naught R. This is the case. Now, if so my total energy that's here, it can be subdivided into three energies. One is kinetic energy of electrons, orbital motion, kinetic energy of electron due to radial motion, then the potential energy of this electron. So to say, if I write down the total energy for this electron, so what would it look like? What would it come? So, so E can be written as kinetic energy radial. Okay, so say radial plus kinetic energy orbital. Okay, let me write orbital, then plus the potential energy. Okay, so potential energy that we have here is negative, so I can think of E equal to K radial plus K orbital plus minus E square by 4 pi epsilon naught R. So inserting this term that we have here into the Schrodinger's wave equation in terms of R, what we will get. So what we'll do, we'll drop this down into this equation. Okay. So what we'll get is oh no. So what we are going to get is 1 by r square d by dr of r square dr by dr plus 2m by h cross square times kinetic energy radial rad plus kinetic energy orbital rb, then what we will have minus h cross square by 2mr square times L times L plus 1. Okay. Times this is all multiplied by the wave function r, and this equation gives us 0. Right now, if we see for the terms that are here inside. Now, if the last two terms that we see here in this bracketed form, what we see is that if we cancel down this with this. Okay, so if we cancel down the orbital kinetic energy with this whole term that's out here, what we will be left with is the differential equation in terms of R completely. We will be left with the differential equation in terms of R. That should be the case, because if this is equal to this, we will have 0 here, and everything will be in terms of R now. So what makes this differential equation the very consistent equation is that what I do is this kinetic energy orbital is equal to this number h cross square times L plus 1 divided by twice mr square. Okay. Now forget about the differential equation in itself. Now let's go with this condition that makes it possible to have a differential equation for the wave function r purely in terms of r. So, to move from here, what is this orbital kinetic energy? So that is 1/2 of mv orbital square. So this v will refer to orbital, and I can think of angular momentum, and angular momentum is mv orbital r. All right. So what will be k orbital? What will be k orbital? Will be simply, it will be L square by 2mr square. Easy. Okay, so we have 1/2 of m, and v orbital square will give us L square divided by m square r square, and 2 will come down. So if this is the case, I can use this result in this equation that we have. So what will I write? This L square by 2mr square is h cross square L times L plus 1 by 2m. Here is 2mr square. Yeah, here is 2mr square. Okay, so here is 2mr square. Because we have to take the square of the orbital velocity here. So here it is 2mr square. The 2 will cancel. So we will have the total angular momentum that will be under root of L into L plus 1 times h cross. So this is what we wanted, and this is which gives us the total quantum number L, and this L is restricted to 0, 1, 2, so on and so forth to n minus 1. And so to say here that this h is the Planck's constant, where we understand that. And if we go back to the macroscopic planetary theory, planetary motion, as in case of energy of the quantum number, describing the angular momentum, is so large that it's difficult to separate out the two discrete angular momenta states experimentally. So this result gives us the total orbital angular momentum of electron, and we have the orbital quantum number. And so to say, L having value 0, 1, 2, and so on and so forth. For 0, there are symbols S, P, D, and F, and these S, P, Ds, and Fs, they correspond to these numbers, like sharp and all of these things, what we call them. So these are the orbital quantum number states in terms of this S, P, D, and F. So here we would like to stop in terms of this orbital quantum number, and then let's see. We will go with the next video for discussion on magnetic quantum number. Okay, goodbye. Have a nice time. Bye.